Hola. I'm starting to learn Spanish since I've been here. Been here for 3 days, so I picked up about 4 words so far. So, long way to go. Yeah, I want to talk to you guys a little bit about secure communications in the modern threat landscape. Everybody's aware of the news reports in Ukraine and the conflict with Russia, how there's a lot of jamming and that type of thing. There's a lot of spoofing. There's a lot of attacks that are going on in the cyberspace. I work for a company called Aeronix. We build radio platforms for the military and for secure industrial complexes. Got 23 years of experience in rail and building control systems, all kinds of different systems from remote control locomotives to inside of yard shunting type of systems. So I actually work with one of our colleagues who's also a presenter here at Wabtec Corporation, formerly GE Transportation. Some of our systems that we have, the radio systems, we have them in space. We have them on board the F-35, some of the drones, and then also some of the attack aircraft. The F-16 is an attack aircraft in the NATO world. In the United States, it doesn't have a ground role. But we do 2 different things. So we have, mission systems is mission planning and that type of thing, and then data recording on board the F-35, so they can come back and determine how well the mission went and how well their airframe performed. And then we also do C5. Sorry, now it's C6. It started out with just command and control, and it was C2. That was about 8 years ago, and now they just keep adding on to it. So you see C6 this year, you'll probably see C7 next year. So just keep adding more and more stuff to it. So now it also includes intelligence, surveillance, and reconnaissance. So that's ISR. Oh, went the wrong way. All right, so the meat of what we really do. We develop waveforms. So waveform is just a modulation scheme that's used on a radio link. We do everything from QAM 6 or QAM 8 to QAM 256. We do a lot of quadrature modulation as well, amplitude modulation, some unique schemes that we've got I can't really talk about, but we're constantly involved and constantly being asked to perform and build new waveforms that are unique. So it's that's going to play into what we're talking about today. We also do cryptography and information assurance, especially for the SATCOM with the HAPI. We put that together. And then network and software-defined radios. We use those software-defined radios both in the military and the industrial context. The last side here is variable message format and improved data modem. It's a way for soldiers in NATO countries and our country as well to be able to communicate to each other when they're not using voice. So it uses the same voice channel, but it transmits data, it transmits information that they need about their allies and who's going into the battle. So that's actually the product line that I manage. All right, so all that's out of the way. That's my sales pitch that my boss said I had to do before coming over here. But I want to talk to you about low probability of detection and low probability of intercept and why these things are important. I got to tell you a story. So I used to live in Texas, and Texas has a lot of wild creatures out there, right? And I woke up at 3 in the morning, and it sounded like there was a couple of 6-year-olds running around in my backyard. I heard this squealing going on. And I'm like, what are these kids doing out this late at night, right? So I run outside. Ended up it was a bunch of coyotes. They had killed something, but they sounded exactly like children. So I just want to. That's the concept here. You may be able to detect something, but can you discern what it is? So low probability or probability of detection is knowing what a signal is and seeing that in a spectrum analysis. Intercept is actually understanding what you're seeing. So, like I said, I don't really speak much Spanish, but I'm learning now. So, so if you have a signal and it's being transmitted between one of your IoT nodes and maybe your control system, and you need that, one of the most difficult things someone could do to you is to jam that signal, whether it be NB-IoT, whether it be LoRaWAN, whatever. And that's a bad thing, because especially if your system's designed such that you need that input, or your system goes all the way down. So it's a jamming aspect. This you can see someone raising the noise floor here. If those two signals and you lay that over the top of it, there's no way you could demodulate that coming out, unless you knew exactly what the noise pattern was, but that's a whole different story. Spoofing. Anybody know who this guy is? Jeff Dunham. So spoofing is, trying to pretend like you're somebody else, right? So I think ventriloquists are kind of really good at that. But yeah, the most common case is where someone pushes a position somewhere else. So this could be bad if you got a control system that's relying on its position to make decisions, especially safety decisions, whether it's going to come in the rail industry, whether you're going to come to a breaking point before you pass a switch, or hit something or derail. So super important to be able to see spoofing and be able to mitigate it. All right, this is a test. Does anybody know who this is? Who said that? Okay, Mark, can you give her the prize? There we go. Yes, this is Hedy Lamarr. She was an actress in the 1940s. I think she played alongside Clark Gable and a couple other people. Not only is she gorgeous, she's really intelligent as well. So she came up with a scheme called frequency hopping. And frequency hopping, what it does is it just goes, your receiver and your transmitter know the hopping pattern, just like a piece of music. That's what inspired her. She was playing Fur Elise. And then she said, why can't I do that on my radios? Why can't I just, if I know what frequency it's going to be, like the tones, and then track along? So frequency hopping is good for a couple of reasons. You'd have to know the hopping pattern to get the full information out. You can do a max hold on a spectrum analyzer here, and you'll see that somebody's doing it. But after you see it, you're not going to be able to discern it. You'd have to figure out which pattern it's going to go in. This is what it looks like, about 30 different hopping frequencies. They've become a lot larger. There's ones with thousands of hopping patterns in there. And to an attacker, it looks just like noise. So you don't even know it's there. So that's kind of that's that low probability of detection, and definitely a low probability of intercept. So this communication scheme is widely used in both the US and our NATO allies as well. So the first use case of it was a radio control torpedo. The British were jamming the Germans' torpedoes, and because they were trying to control them from their submarines wirelessly. And to get around that, they came up with this frequency hop. They borrowed the patent from, not borrowed, I guess just stole it, but from Hedy Lamarr. So very interesting. I think that's how they were able to do what they did. All right, so what's a requirement for resilient waveform for critical industry or infrastructure? One of the things you have to look at is, what does your signal look like, right? So if you got this signal, it's kind of big and sloppy, right? You got a main lobe and you got a bunch of side lobes, and your side lobes are coming up really high. So your signal to noise ratio there is not that great. Information's in the side lobes, so someone can hear that. So it increases your detection surface. So if I was to take a cursor, oops, and I was just listening right here, I would start to hear the signal. If it was voice, I'd start to hear the voice. It would be staticky. But then when I got here, it would be clear. So you want to try to reduce these side lobes, so you're only transmitting in a very, very, very narrow window. And the reason you want to do that is, one, you can apply that to frequency hopping technologies. But two, it's a smaller window for someone to look at. Because when you're trying to scan for an adversary, you have to look at the entire spectrum at the same time, because you don't know what frequency they're going to be at all. So this is an important thing. If you can hide your transmissions, then you definitely have a chance of not being spoofed or jammed. Another technology, or another methodology, I should say, is to, instead of your antenna being, this omni type of antenna, to start using beamforming. Everybody's aware of the phased arrays that, are being used by SpaceX and those type of things. You don't have to have mechanical steering on your antenna anymore. It's not patch antennas or the, pointing antennas. But you can do that with the phased array. And this allows you to just basically talk directly to the intended receiver. Some of the GPS spoofing and some of the GPS denial that's been happening, the way that it's being approached to get around that is to transmit position data directly from the satellite to the ground forces. So there's no way for you to know exactly where that's coming from. It's not pointing. The signal-to-noise ratio is super high versus someone just blasting at the 1.5 gigahertz frequency for GPS spoofing. All right, so just a couple of different things here. Just thinking about this from the low probability of intercept, low probability of detection standpoint, there are a couple of IoT radio waveforms that are being used. Biggest thing I'd like you guys to take away from this is that there's standards and then there's resiliency, right? So the more standards are, the easier it is for someone to create a way to attack it, right? So everybody knows how it works. Bluetooth is a perfect example of this. Bluetooth also uses frequency hopping, but they use it to kind of coordinate inside of or move around so they're not constantly being blocked on a specific frequency. However, everybody knows the hop patterns. It's in the specification. So it's not as resilient as it could be. Now, if you were able to choose your own hopping pattern inside of Bluetooth, it would probably go up to a higher point. NB-IoT is we put it at the moderate, the infrastructure that it has from all the cell towers and everything. But LoRa is good, but LoRa is chirp spread spectrum. So you got an up chirp or you got a down chirp, and it kind of codifies the symbols. The symbol has all the bits in it, and then you figure out where it's at. But you have to choose a frequency, and each country has their specific frequencies for that, and that opens it up to someone knowing where to jam, knowing what frequency it's at. So, all right. So, resilient improvement techniques. So detection is one of the biggest things. So obfuscation, hide. If you have a critical data link that you need to, talk to a sensor, whether it's a nuclear power plant or an oil refinery or whatever it may be, you don't want people to know what frequency you're transmitting at between your sensors and your nodes. Just keep it hidden. Other thing to do is sensor fusion. So I wouldn't rely on that input and that input alone. GPS is a good example. You can use dead reckoning in addition to GPS and GNSS. You can use all kinds of other things to determine whether or not that someone's spoofing you and trying to push you out into a different position. RF alternates, so other ways to communicate. If you've got some kind of a backhaul, you might want to have that as a backup, and then if those sensors don't agree, then you could declare spoofing or declare some problem with it and fall into a safer state. And periodicity. So I know how many people are software engineers here? Yeah, so a lot of software engineers don't like to do random. So if they're going to send a message, they want to send it every so often, so it's 30 seconds or 60 seconds or whatever it may be. Periodicity actually, it kind of helps you detect. So I can just watch and I can see where that signal is coming from. But if it just comes at random times, just completely random, then it's more difficult to find. It takes a longer time to find it. Spoofing and jamming defense. I think I've talked a little bit about this before, but data validation is very important. If I all of a sudden have my position tell me I'm 3 miles away and it only took me 2 seconds, well, I don't have that kind of footwork there, so I can't go that fast. So that would be invalid. And then the common filter as well inside of sensor fusion. Encryption is also very important. The slide I showed before, it looked like I was kind of bagging on some of the other waveforms. No, they're good if you have the cybersecurity on top of it, But from a pure spoofing and pure jamming, there's nothing really you can do about it. This is something that's new. So now that you have this zone of silence between Ukraine and Russia, those areas, you're starting to see these fiber optic drones. It reduces their overall payload for their weapon system, but it allows them to attack without being jammed or pushed. So has anybody else seen these guys? They're just starting it. Yeah, and they go I think about 2 kilometers with that spooling mechanism. So really interesting. All right, let's see. All right, got questions? Hope I didn't go too fast. All right, thank you.